All right, welcome to Chapter 9. In Chapter 9, we're going to add a third branch to our understanding of calculus. So we've learned differential calculus in Calc 1, and then the end of Calc 1 and most of Calc 2 so far has been about integral calculus. So we're going to add a third branch, which is infinite series. Okay. And series are really useful. So they're useful for things like integrating e to the negative x squared. So if you think about this one for a moment, you'll realize we can't do a u sub on here. There's not really a way to do integration by parts. And so one of the things that we can do is we can do a series expansion of e to the negative x squared, and then we can integrate that term by term. So that's what we're going to look at in Chapter 10 with Taylor polynomials, which are based on series. So that's kind of where we're going to be headed with this. There's also something called a Bessel function, which is a sum of series, and those are used in mathematical physics and chemistry. And then some other applications include things like optics, special relativity, electromagnetism, and then analyzing phenomena. So we'll take another look at that in Chapter 10. Before we kind of get going into this chapter, I want to take a look at kind of two really interesting examples of infinite series. So the first one is e to the x, and e to the x is written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And so the interesting thing about this is it shows that e to the x can be written as an infinite polynomial. And we'll actually look at how that's derived in Chapter 10. So you don't just have to take my word for that. But that is kind of cool that we can express things like e to the x, sine of x, natural log as infinite polynomials. And then this other series is the Gregory Leibniz series, and this is the value of pi over 4 is equal to 1 minus 1/3 plus a fifth minus a seventh plus 1/9. So we have all these odd integers along in the denominator. So what that shows is that pi is related to the reciprocals of odd integers, which is kind of, a really intriguing fact. So we'll take a look at that too as we get going to Chapter 10. So infinite series are going to provide a new perspective on functions as well as interesting numbers. Okay, and one of the tools that we're going to be using to analyze these series is limits. So you saw limits at the very beginning of Calc 1. We used some limits with our integrals and we looked at improper fractions, and so we're going to be doing some more limits. Primarily, we're looking at limits as n or x goes to infinity in this chapter. All right, so in order to kind of make sense of what a series is, we're going to take a step back. We're going to start by defining what a sequence is. All right, and I'm going to grab an extra piece of paper here because I'm writing with a big pen so that you can see more easily what I'm writing, but it then doesn't leave a lot of space to fit stuff. So a sequence, we're going to define that as an infinite, and there are finite sequences, but in this chapter we're going to be interested in infinite ones. So an infinite list of numbers in a specific order. And you will often see a sequence written. You could see it written as just a sub n. You could see it written as a sub n equals f of n, so some sort of function. We'll come back and talk about that in a second. You might also see it done with curly brackets too. Okay, so all of those are different ways of expressing that we have a sequence. So our sequence is an infinite list of numbers in a specific order. It's often defined by a function. And we're going to call that function f of n. So this isn't f of x, but this is f of n. And so let's talk about what that n means. So the n is our domain, and our domain here is the natural numbers. Okay, and they're often, natural numbers are written with this uppercase n that has an extra bar on the back. So that's going to be our domain. So when we plot these, what we're looking at is a series of points. Okay, so that x represents all real numbers, but we're going to use an n, and so we're only using the natural numbers. So looking at 1, n is 2, 3, 4, 5, and so on. Okay. Let's define a couple more things here. So our first term is a with a little 1. Okay, the second term would be represented by a sub 2. The nth term is a sub n. And then the term after that is going to be a sub n plus 1. So when we come back, we'll look at actually writing out some of the list of the numbers.